Okay. So in our last lecture, I introduced the binomial random variable. Basically, binomial random variable is a bunch of yes-no trials as part of a larger experiment. Okay. So in this case, what we typically do when we describe the binomial distribution is we say x comes from some binomial distribution and is parameterized by two numbers. One is the number of trials, which is n, and then p is the probability of success in each one of those trials. And we can describe for this binomial, right? Usually we care about how many successes did we have out of the n trials. Ooh, and actually there's a mistake right here. This should be an x. And so based on that definition, it's pretty straightforward to sort of make sense of the probability distribution that we have. So typically what we can do is this function right here tells us what's the probability of getting x successes given, so the way you want to read this semicolon is like a given, n trials where the probability for success in each trial is p. So that was pretty nice. From there, we talked about the cumulative distribution function. And what that allows us to do is start asking questions like, what's the probability that the number of successes is less than x? And I don't know why I got that wrong too. It's less than x. Man. Last Thursday was a bad day. Oh, I see why. That's wrong in my notes. Okay. So use it, and the only way that we can calculate this is by basically adding up the PDF one at a time, which isn't particularly nice, but it's sort of the world we live in. At that point, I think we demonstrated how you can calculate this probability distribution in Excel. That way you don't have to do it manually. Okay, so a lot of these things, just use Excel, that's fine. That's what it's there for. Okay, so now this sort of gets us to our next question. When we first introduced the idea of family of distributions, or in fact, probability distributions, we always cared about two values, kind of. One of them is the expected value, and the other is the variance. And what I mentioned to you was that for these family of distributions that we use all the time, you can just look these values up. Somebody has spent the time to derive the expected value for a lot of these distributions. So at that point, I might as well give you them. And so we have a proposition. Okay. So if x is coming from a binomial distribution, and parameterized by n and p, then the expectation of x, again, this is the number of successes that we expect to see, all right, the long one average, is given by n times p. Okay. Meanwhile, the variance is given by n times p, 1 minus p. All right. So a while back, and I sort of mentioned this, so in some ways statistics is a weird field for me, but I talked to you guys, or I mentioned that sometimes you'll see people use parentheses here, and I wasn't quite sure why that was, right? And why use, the book uses parentheses here, but blocks there. And so I did a little bit of research into this, and actually thought it was really, really neat. So usually, okay, if you guys talk about functions, let's say we had some function of x, right? You would write it like that. And the key point here, so this is sort of an aside, so don't worry too much about it. The key point is that x is a number, whatever that number might be, okay? It doesn't even have to be a number, right? It could be like dog, cat, school, right? It's an object, right? And so when you have this function, you're passing the function an actual object, okay? So there's some weird function notation that I always forget because I don't use. Let's see if I can find it. No, that's not it. I'll find the function notation at some point. Let's see if they have it. No, I don't like this. Okay, so I'll show you some mathematical function notation. Anyways, the key point is that if you have a function that takes in an object, we could say, then you do something like this with the parentheses. All right. Now, in our case, what we're passing into the expectation is not an object. Okay. Does anybody remember what a random variable actually is? It's not a number. It's a function. Yeah. So when you take a function of a function, so this thing here is actually called a functional. Okay. So a functional is any function that operates on functions. Okay. And so mathematicians sometimes like to distinguish between functions and functionals. And that's why you see them using the square bracket for the expectation. Now that leads me to my next question is, why doesn't the book use a square bracket for the variance, right? I don't know. But I thought this was kind of interesting. So if you ever want to know, if you're ever studying sort of physics, advanced physics or some advanced mathematics, and you see a bracket, you should think the thing inside of it is actually a function. Okay. Okay. All right, so we know what the expectation is. We know what the variance is for a binomial random variable. Now, based off these binomial random variables, we actually have a few related distributions that are kind of nice to work with. One of them is hypergeometric. Okay, all right. So hypergeometric is kind of like the brother to the binomial distribution, or it's very closely related. So in the case where we are talking about, let's say, sampling cars to see if they passed emissions or not, right? One of the underlying assumptions there is, let's say we sample 20 cars per day, is that the 20 cars we get are unique cars, that we haven't sampled them before, okay? Because if we're sampling the same, fail the exam, you come back the next day and you keep coming back because you keep failing, that sort of distorts your statistics. So that's one assumption we made, is that we're seeing unique cars every time. The other assumption that we're sort of making is that the total population of cars is substantially greater than the number of cars that we actually see in a given day. Okay? So traditionally, if you're making that approximation, you're allowed to do it. I always forget what the exact number is, but they always have it. Let's see, I wrote it down because it's a little bit weird. Oh, okay. We can write it differently. As long as your sample size, so this is like your sample size, is substantially smaller than your total population. So again, in our car problem, we could assume a state maybe has like 10 million cars, and we're sampling 20 cars on any given day. Okay. And so we could pretend that, hey, we're not resampling the same cars because it's so unlikely that it actually happens. All right. So hypergeometric basically gets rid of this assumption. Okay. So this is no longer true, that the sample size is substantially smaller than the population. Okay. So you can imagine this would be the case if I have like a bag of presents, right, 20 presents, and I say grab 5 presents from them. How many, and with 20% chance, it's a good present that you like or it's a bad present, right? That would no longer be a binomial distribution because you're taking out about 25% of the presents at any given time. Okay? So in that case, we want to use something called a hypergeometric distribution. Okay? So in this case, we have a few specific parameters. One, the population consists of n, right? So we'll have it predefined. Okay. So of these n elements or objects, whatever you want to call it, m are successful. Oops, just one L. Okay, and of course this and finally a sample of n are taken. So for this particular hypergeometric distribution, I can give you guys the PDF, all right? And again, it's parameterized by n, m, and n. So if you actually wanted to work this out, the PDF that I'm going to give you, you could do it from the counting techniques we learned. But here we're trying to make life a little bit easier for you. So the probability that x is equal to x I mean, you can write this a few different ways. Uses the notation H for hypergeometric, for hyper, I guess. Okay. And it sort of makes sense. What we're seeing here is out of n objects, big N objects, you're going to choose little n of them. How many different ways can you do that? All right. And then here we're talking about, okay, once you've drawn m objects, how many of them will be successful versus how many of them will not be successful? And so that combination, if we do the ratio, gives us the probability for a hypergeometric distribution. Okay. More so, we can sort of figure out what the expected value is. It ends up, it's just n times m divided by n. Okay. And the variance it's kind of ugly. And these are fractions, not combinations, just so you're aware. So if you want to rewrite this, Same thing, right? So I don't know which way is easier for you. Okay, so let's sort of do an example problem with this so it makes a little bit more sense of what a hypergeometric distribution is. Okay. So we're going to do a problem where we're going to be flipping some coins. Okay, so let's say we have 10 coins. All right. Of those coins, 7 are fair. So that means they have a probability of 50-50 being flipped. So my question is, what is the probability of grabbing 3 coins in which at least one coin is unfair? Okay, so what does this problem sort of represent? So let's say I'm some street hustler. I can keep 10 coins, right? And I can go to you, hey, come play a game. We'll flip for money. And I know which one's fair, right? So I have a whole bunch. But let's say I marked one of them so I know which one's fair. And I go, hey, look, I got this fair coin. Watch. Boom, 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 boom. I show you a bunch of times if we flip it back and forth. Hey, it looks like a fair coin. All right? And then I say, here, let's do this. I'm going to grab 3 coins. And if more heads show up, you win. Or if more tails show up, I win. All right? And you can imagine that you could do this in a way where it seems like an even game. But the reality is it's not, because some of the coins are unfair. Okay? All you need is one of those coins to be unfair if you're going to be flipping 3 coins. And you'll always, on average, beat this guy. All right? So you'll hustle this guy. All right. So what we're asking for when we solve this problem is we're asking what's the probability. So we should define our random variable. Okay. Okay, so here our random variable x is going to be the number of fair coins of 3 randomly drawn from the 10. Right? So what we want to calculate is what's the probability that x is less than or equal to 2. Okay, so if we calculate this probability, at most 2 coins will be fair and 1 will be unfair. Alternatively, we could write this as 1 minus the probability that all 3 coins are fair. Okay. So either one, yeah.
Probability of x less than or equal to.
Oh, this is a 2. Yeah. Because we're trying to see if 1 coin is unfair. So we could rewrite that as 1 minus the probability that all the coins are fair. Okay, so that's pretty easy to calculate now that we have our equation. And so we can plug that in. Now, so first I'm just going to write the equation so we have it and we'll start substituting stuff in. Okay. So in this case, n is equal to 10, which is the total number of coins that we have. M is equal to 7. And then for this probability, n is equal to 3. So if you go ahead and make those substitutions in here, then you'll get your answer. Oops. Missing one. Ah. Mn. And of course, x is equal to 3. Yeah. Okay. So again, big N is the population. M is the number of successes in the population. N is the number of samples drawn. And X is the number of successes drawn. Okay. And so we can sort of plug all those guys in. And I'm not going to go through the calculation. Because again, I think there's something that's best left to Excel to do. Okay. So this is sort of a good problem. And again, the thing that makes this a hypergeometric distribution is that the population size relative to the number of sample size, they're relatively close to each other, right? So only if your sample size is less than 5% of the population, in that case, you can use a binomial approximation. Okay, if you don't have that, then you probably want to use a hypergeometric distribution. Okay, cool. Any questions on that? All right, awesome. All right, so the next really common distribution, is something called the negative binomial distribution. And in fact, this is one that we've worked with before. Okay? So in this case, we still have a sequence of independent trials. All right, so each trial is a success or failure. Okay, and we'll still define the probability of success is P. Okay. But now, the one key difference that we're going to make from a normal binomial distribution is what we want to know is we want to know how many trials we need to reach a certain number of successes. Okay, so put another way, all right, so our experiment's going to continue until we have a total of R successes. So the problem that we did that was very closely related to this is how many kids do I need to have until I have a girl? Okay, in that problem, the parameter R was equal to 1. Okay. But you could imagine, hey, I need to, so the example we'll sort of do is I'm going to ask people to join my soccer team. Right? I need 11 or 10 other players on my soccer team. How many people do I have to ask until I have a complete team? Right? So that's sort of the question. All right. So again, we're going to go through the standard procedure where I give you guys the expected value, the variance, and the PDF for a negative binomial distribution. Okay. So here our negative binomial is going to be described by two parameters. One is the number of successes we need, and then P is the probability of success on any given trial. So the PDF for our random variable x so we usually denote the PDF function as NB, right, as a function of x given R and P. And you could actually derive this from all the counting equations that we did before, and it sort of makes sense. And it, this sort of looks like what we calculated for the how many births until a girl. But now we're generalizing it to the case where R could be greater than 1. The assumption is that when I write this probability, again, the idea is that x has to be a whole number, okay? Because that's the number of tries I have, right? You can't have like 2.5 as a random variable, so the probability of that happening is 0. So in this case, for discrete variables, your x takes on specific values. Okay. So the expectation for this random variable is given by R times 1 minus P divided by P. All right. And well, we're given that for the variance. Again, if you want to calculate this by hand, you can certainly do so. We know what the equation is for expectation. It's just the sum of x over the space. So in this case, well, not 0, because you have to have at least one experiment. Actually, that would still work. You could have put 0 here because you would have had 0 times the probability. But it's just x times the probability of x occurring, right? So if you were to go do that, you could certainly derive this equation here. Likewise, you could derive the variance equation. Okay. So because these are common distributions, somebody's done the work for you. But I think it is a good idea to sort of work through these if you ever have the chance. But I understand why you might not. Okay. Okay, so let's sort of apply this in practice. Let's do this soccer player problem. All right, so our goal is to recruit 10 soccer players. Okay. All right, so a standard team has 11 players, but we're going to assume that you're playing or I'm playing, so we just need 10 more. So we're going to recruit 10 more soccer players, and each person we recruit, the probability of them joining the team we'll say 75% of my friends who I ask agree to join my team. Okay. In reality, that's a much lower number, I think, for those of you who have ever tried to form a team. What do you guys think the probability is, actually?
Like
50%?
15.
50? Okay, yeah, that sounds more like it. Yeah. 20, yeah. It's pretty low, right?
Yeah, if you add strangers, it's like 2%.
Yeah, so this is sort of, I mean, like, this is a real problem. So we use this when we're doing, like, when we're trying to figure out, like I've worked with people who have run like human subject studies, right? And we'll always be like, we need 40 participants. We know the response rates of participants is like 2% or lower, right? Like, how many people do we have to reach? Like, if we want 100 people, at that point, what it means is like, well, you're running into all sorts of issues, which is like, what fraction of the population has the characteristics that you want, right? So if I'm just doing a simulator, like a flight simulator, and you don't need any skill, hey, all of you would work, my response rate might be 5%. Now, let's imagine you're doing some medical testing and you've developed a drug for some relatively rare disorder, right? It becomes a lot harder to recruit patients. Even if you're like, if you're working with a disorder that is relatively common, so let's say depression, if you work out, like let's say you need 100 folks, right? And you assume 5% of people with depression would want to do the study, or maybe it's probably even lower, 1%, right? All depends. And then you have to consider what fraction of the population is actually suffering from chronic depression. Your probabilities get lower and lower, and that explains why when you're riding the bus, you see signs for, do you want to be part of some medical study, right? Because the only way that you can build the necessary sample populations is if you start advertising to like 100,000 people. Okay. So this is a good example of how you might use that if you want to figure out, how many people, or let's say you have a business and well, in order to make this business self-sustain, I have to have at least 1,000 customers per year. What does that mean in terms of your marketing efforts? Okay. So how many people do you have to reach via television, newspaper, internet, and all that stuff? Okay, so let's actually do this problem. And so first, I'll ask simple question. What is the probability? We only have to ask at most 20 players. Or 20 persons, right? Okay. All right, so here, again, R is equal to 10, P is equal to 0.75. All right, so at this case, I'm going to tell you, well, you know the equation, and right off the bat, you should see it has some combinatorial thing, so it's a little bit messy. Just toss it into Excel, okay? But I want you to be a little bit careful here, because like most things in life, Excel is sometimes a little bit weird. The function doesn't necessarily, I already have it open. Let's see. Excel doesn't necessarily format it in the way that you want. Excel actually does it backwards. Or at least I think it's backwards. Is this it? Oh yeah, that's it. Okay, so I'm gonna redo what I have. If you want, you can ignore the numbers or not ignore the numbers. Okay. So the way Excel kind of works is the function is this negative binomial dist, okay? And you're gonna give it 3 numbers. Okay, so let's say these are the 3 numbers I give it. The way you want to read this, this is the probability of one person saying no before 10 say yes. Okay. All right. So in this case, if I want to know what is the probability that we have to ask at least at most 20 players, that means 10 people are going to say no. Okay? All right. So what I'm going to do here, if you can read it. So I'm going to have a column called num say no. All right. And I'll have 0, 1, 2, 3. We can go all the way down to whatever number, doesn't really matter. I'm going to go down to 20. Actually, let's do this on another sheet. So this is the number that are going to say no. All right. And so what we do need is we need the number that we want to say yes. All right, so those are successes. We want 10 yeses. Okay. And we want the probability of a yes or success. 0.75. Okay. And so we just use this negative binomial dist. There's two different functions. I think one is the old way of doing it, one's the new way. And so we're just going to feed it the column to the left, the number of successes we need, the probability of success. And what I'm going to do is I'm not going to ask for the cumulative. I'm just going to ask for the probability distribution. Oh, did I not? Oh, yeah. Thank you. So what do I need to anchor? B1 and B2? Yeah, there we go. Yeah. So we can calculate those probabilities. All right, so let's make a nice little pretty chart. Why not? Okay. All right, so the most likely scenario in this case, so again, most likely is just given by highest here, is that I ask, I don't know, somewhere between, 3 or 4 people? So, 3 or 4 people say no before I fill out my whole team. Okay, so I'd have to ask 13 people is the most likely scenario. Okay, if we want the expected value, right, then all that we're doing is how do you do that column sum again? Sum product. Yeah, there we go. We're going to do the sum product of this guy times the sum product of that guy. Now this is only going to be approximate because I'm only doing the sum up to 21 here. Like really I could ask 50 people, but it's just unlikely. All right. So what this tells us is the expectation is about 3.3. All right. Actually, let's move this equation over. All right. Okay, and in fact, okay. So let's try to work with reality. So I think you guys said about 15% say yes. All right. Or yeah, 15, is that a good number? Why not? Sure. So then the question is, how many people do we actually have to ask? Clearly it's going to be more than 21. So I'll go ahead and fill this out to 400. All right, and let's see what happens. All right. So if you're building a soccer team from scratch, 15% of people say yes, you're going to have to ask about 57 people before you make a team. Does that sound about right? Sounds about right to me, at least in my experience of building a team. Right? Yeah, I used to be part of the student club, and I think we had about 60 to 70 people. And this was, yeah, that's about right. I would say we probably asked about 50 people in the club to join. Yeah.
This might be dumb because I'm pretty sure it's not that easy. But like, if you wanted to just double, like if you wanted 20 people to say yes, could you just multiply it by 2?
No, I doubt it. Let's see. Let's do this here. Yeah.
It's at 56 right now.
Oh, it does. Is that right? Man, I'm surprised. I am very surprised. Here, let's do this. Oh, well, it's not really set up to do it. Insert. So I'm going to take this equation. I'll stick it there. Oops, no. All right. And we're going to vary this guy. Oops. Okay. A1. So what's changing here? Number of people to say yes is B2. We're going to keep that constant. All right, so hopefully if I did this right, A5. All that we should be changing is the number of people to say yes. Okay. And I will fill this down. That's a very good question. All right, so what I'm going to do is I'll plot this 2 guys and we'll see whether that's the case. Oh, I guess so. There we go. It's linear. That surprises me. Okay. I thought it wouldn't have been linear. Well, goes to show. Okay, good question. I don't know. That really surprises me. That does surprise me. Okay. Does that make sense in the equations?
We're varying R, right? When we change.
Yeah.
Yeah, since the probability stays the same and you're only changing R, and the expectation is equal to R times.
Yeah. Yeah, that's right. So that makes sense. Yeah. Oh, that makes perfect sense. Yeah. So we see it proportional to R. Yeah, there we go. Okay. I guess the math does work out. That surprises me. You know, whenever I see combinatorials, I never expect linear behaviors. Okay, so this is kind of a fun little distribution to work with. Okay. So that sort of takes us to our next distribution. And the last sort of discrete one that we're going to do. So in my world, this is actually the most, outside of the binomial distribution, this is actually the most important distribution. So those 2 are probably usually the 2 most useful ones. All right. And so this one's called the Poisson distribution. I don't know if it's named after a person or if it's named after a fish. Some of these distributions have really funny names, how they... Oh, it was named after Poisson. Okay. Simeon Denis Poisson. Okay, French guy. Cool. What a funny name. So another good one that I really like in terms of distributions, is there's something called a Dirichlet distribution. Okay. Do any of you speak French? No? You speak a little French? So if you were to speak, so Dirichlet is named after a person. Okay? So there was this guy named Dirichlet. And he grew up in France, but oh no, sorry, take that back. The name is French, right? Dirlichet is a French name. But the guy grew up in Germany, okay? And so if you pronounce it with a German accent, I think it's like Dirlichet. You actually pronounce the T. Let's see, yeah. And his name makes it even more confusing on what to do, because you see his name is Jean Peter Gustav, which is like a very German name, right? But then he has this French part. And so you can see there's actually, well, this gives the German pronunciation of his name. Now the issue is there are no more Dirlichets in Germany. He was like the only one ever, okay, or his family. And so they can't even ask German people like, hey, you have the same last name as this guy. How do you say your last name? And so there's this big, I don't want to say like fight or there's this discussion of how do you say that word, Dirlichet, okay? For those of you, are any of you guys computer scientists? CS? No? All right, so in CS, the common issue is with this word. It's a GIF?
Yeah.
It's not a GIF?
No, it's not.
Because I think it's a GIF.
GIF is long.
Say again?
Anyone that says GIF is long.
Yeah, that might be the case. So it's the same idea here, right? People.
The inventor of it pronounced it GIF, but it stands for graphic image.
Yeah.
Like GIF.
Yeah. I call it GIF. That's how I learned it. But I understand this guy called it GIF, right? Which doesn't make any sense to me. But okay. You know, who am I to argue? Yeah. Okay. Anyway, so Poisson. Okay. This is probably one of the most useful distributions, at least for discrete distributions in engineering. Okay. And that's why I do want to spend maybe a little bit more than 5 seconds. Like, I think most classes basically just say read the chapter. Okay. But, you know, in this class we go into a little bit more detail, I think, than others. So the nice part about this Poisson distribution, or the place where it's typically used, is that it actually describes the number of events in a fixed interval. Okay, so these types of problems are all over engineering. So I think I mentioned to you one, which is the telephone operators, right? They wanted to know how many telephone operators they needed for a city. That is closely related to a Poisson distribution, right? Because you can think, how many phone calls do you get in an hour, right? So that's going to deal with, you know, how many operators do you need? People use Poissons for all sorts of things. Like in my research, I use them to count how many aircraft enter into an airspace or land at an airport in a given day or a given hour. People use them kind of poorly, but sort of to predict how many like disasters or hurricanes you expect to see within some time frame. Okay, so this distribution is used everywhere. Okay, all right. So the definition of a Poisson, at least in terms of the probability distribution and how it gets parameterized. All right. So for some random variable, we write that it's drawn from a Poisson. So sometimes you'll see people just write Pois, I guess. If you were to do that. Or you could write out Poisson, that'd be fine as well. And it's parameterized by this guy lambda. Okay. So the key here, lambda has units of events per unit time, right? So phone calls per hour, or phone calls per minute, whatever you want. So In this case, the units are actually really telling of this distribution when you work with it. Yeah. Okay, so the probability distribution for a Poisson distribution, it kind of looks weird. It's got this weird mix of an exponential, a factorial, and another exponential, right, or to the power, I guess. It sort of mixes in all our favorite things. The only thing missing is probably pi, right? But it basically throws the whole kitchen sink at it. The neat part about this distribution, if you go on to, any of you who study operations research or stochastic systems or control theory, the really neat, or signals and communications, the really neat part about this distribution is you can actually derive that equation, right, from making one statement, which is the probability of an event happening in some instant of a time or some very small delta time period is, let's say, a binomial distribution with probability p. Okay, that one statement, okay, that in any sliver of time, so if here goes time, and I look at some delta t, at some probability, okay? From just that one statement, you can actually derive a Poisson distribution. And the crazy part is it holds all over the place, right? In the next chapter, we're going to learn its sort of mirror image, right? So here we're talking about how many events do we have in a fixed interval. You can flip that question around and ask how much time passes between two events, okay? And so that's a continuous random variable. That's something called an exponential distribution. The exponential distribution is super, super neat. So again, it's like how much time passes between two phone calls. The neat part about an exponential distribution is it has this property called memorylessness, okay? So like memoryless distributions are basically work like this. If I haven't had a phone call in the last 10 minutes, the probability that I get a phone call in the next 10 minutes stays the same. Okay, it doesn't matter what happened in the past. Okay, so why is this a neat property? One, it makes math super easy. The other really neat thing about it is that sort of description, one application of it is to describe what we would call, what is it when you live forever? What's that called?
Immortality.
Immortality. Okay. It ends up, so let me maybe posit to you a different way. The lack of immortality means that the probability of your death increases with time. Okay? But what if I were to tell you the probability of your death stays the same no matter what age you are? So this is one description of immortality. And it actually, because of this memoryless property, it's the same thing as an exponential distribution. So the amount of time until you die follows this exponential. The neat part is there are actually some animals whose lifespan is dictated by an exponential distribution. So I think like houseflies have them, so technically they're immortal by this definition. And another one is the things that dig underground and they're blind. Moles. I think moles also have this property. And so there are a lot of people doing research on how do humans become immortal? And they use this definition, right? Our goal is not for you to live forever, but our goal is so that the probability of your death at any given age remains the same.
Just live in 3 days.
Yeah, live for 3. Yeah, so it's really neat. Anyway, so that's the continuous version of this problem, right? So a lot of these distributions, you will find they're sort of like a related distribution where you're looking at the same problem from another direction. Okay, So the neat part about this Poisson distribution is that the expected value is just equal to lambda, all right? And what's even neater is that the variance is also equal to lambda. Okay, so you don't have to do any work here. You can imagine there's a really nice summation here, right? So if you, again, when we're doing the expectation, you can imagine that this series is probably something really, really nice in order for us to just end up getting lambda, right? So consider working it out if you want to have a good time on a Friday night. Okay, so let's do sort of a quick example problem. And again, look, if you want to, I'm not saying ignore what I'm teaching, but like in terms of priority of like hypergeometric and negative binomial, Poisson's way more important to engineering. It will come up over and over and over again in your life, especially if you go on to grad school, okay? And if you're ever dealt or given problems where you see something in terms of how many events per unit time, the first thought into your head should be Poisson, okay? And you can do all sorts of things with it. All right. It just so happens that because Poisson has this property where the expected value is equal to lambda, a lot of the stupid things that people do work out, right? They say, so this example problem, let me give that example. So, all right, so we're going to talk about my email. I made up these numbers. I don't know if they're actually true. Let's say I get a rate of 10 emails per hour. Okay. So if I ask you how many emails do I expect to get in 2 hours, you would probably say 20. All right. In some ways, you're making a lot of assumptions, but the reason why that works is because the expected value of x is lambda. That's it, right? Somehow you got lucky that this summation, right, is equal to lambda, and that you can use that assumption, right? And then you're also using linearity, right? So if I'm asking you how many things showed up in 2 hours, then what I'm doing is email showed up in 2 hours. I'm saying, well, 2 hours, or that 2 hours is how many show up in 1 hour times 2, right? There's a lot of assumptions that go into that, so just be careful. But again, people got lucky because the math works out nicely. Okay, so let's say I get these emails at a rate of 10 emails per hour. So the question I'm going to ask is, what's the probability of receiving 6 emails in 1 hour? Okay. So again, in this case, okay, so our random variable x is the number of emails we get in 1 hour, and I'm asking what's the probability that I get 6 emails in an hour. Okay. So in that case, probability of 6, we just plug in our equation. Lambda x e to the minus lambda x factorial. In this case, lambda equals 10 emails per hour. You'll notice I'm always being very specific about the units here. This is one of those distributions where the parameter actually has an intuitive meaning, right? I'm not going to say that the other ones don't. Like, usually we just saw like P and R, right? Number of successes, probability of success. Probability technically doesn't have a unit, right? Number of successes, well, It's kind of intuitive, or not intuitive, it's sort of not that interesting, but this one's actually interesting, right? Because it does have a more complicated unit associated with it. All right, so in this case, lambda equals 10, x equals 6. What else are we missing? Oh, that's it. Okay, so we can just plug everything in. 10 to the 6, e to the minus 10, 6 factorial. Of course, again, plug it into Excel. There's probably a distribution for that. 0.063. Let's see what the Excel distribution is. Yeah, Poisson distribution. There we go. So they give it as mean. Again, the mean just happens to be lambda, so we can use that. And I'm going to just ask for the PDF here. All right, so there you go. So that actually looks almost, later on we'll learn normal distributions and stuff. That almost looks normal. Be careful about that. Actually, the distribution it's most closely related is a binomial distribution. Okay. So in fact, I think there's an approximation between the binomial and Poisson distribution. All right. We can see what happens as we change lambda. All right, that doesn't look too bad. Now it's starting to look a little bit different. Okay. Oops. 1. We could even have 0.23. There's nothing that says we can't have a fractional value, right? So if I get, let's say, 0.25 emails per hour, that's certainly a thing. That means on average I get 1 email every 4 hours. All right. Hopefully this shows you why you shouldn't approximate a Poisson distribution with a normal distribution. Again, we'll learn about normal distribution, sort of that bell curve thing. But there's a few reasons. One, a Poisson is a discrete distribution, while a normal distribution is a continuous one. The other issue is that normal distributions, all right, so a normal sort of looks like this. All right, it's symmetric about an axis, and it goes infinitely far in each direction. All right, and let's look at this Poisson distribution. All right, this Poisson distribution stops at 0, and it's certainly not symmetric. Okay, so at some points in your life, I'm sure somebody will say, hey, the number of emails you get in a given day approximately looks like a normal distribution. And you'll go, no. It's actually a Poisson distribution. All right? It's just that the lambda is relatively large. Yeah. It's not really a normal distribution. It's a Poisson distribution. So don't make, yeah.
Couldn't you just change that by adding more?
Yeah. No, but still, we still have a few issues. One is Poisson gives you a discrete value. You get whole number of emails, right? A normal distribution could be like 3.5 emails. It doesn't make sense, right? So the other issue is it's still not a symmetric distribution. It gets closer to symmetric. That's certainly true, but it's not.
Yeah, I'm asking the other thing. Like, can you, if it looks normal, can you make it look Poisson by just adding more?
If it looks normal.
Yeah, so like originally we had 10 as the lambda.
Oh.
If we just made it, instead of graphing to 30, made it like graph all the way like 50.
Okay. So let's do that. Why not? We can make it graph as much as you'd like. How do I change this series? Oops, nope. Oh, come on. We'll get this. Select data. Series 1. B4. Okay, we're just going to make a new plot. Why not? There we go. Okay, so this is our plot. All right. So clearly it doesn't make sense to go for this one past 50. All right. This also gives us that other indication that it doesn't really, I mean, it kind of works, but it doesn't. So just my hint to you all, don't be tempted to use a normal distribution for what is a Poisson. Okay? If anything, you could say it's like a binomial, but usually what you're going to say is, hey, a binomial distribution looks like a Poisson. That's really the direction you want to go in. Okay. All right, so we got that guy. Another question we might ask is, what's the probability that the number of emails I get in an hour is greater than or equal to 15? Okay. That's just equal to 1 minus the probability that x is less than or equal to 14. All right. In which case, we have to add up our probabilities, right? So this is not a fun summation. Okay, but if you were to do it, you'd get something like 1 minus 0.91. So the probability is, there's a 91.91 probability, 0.92 probability that I get less than 14 emails in an hour. Okay, so the probability that I get 15 emails in an hour is 0.83, or more than 15 or more. All right, so if you want to calculate this, again, I don't suggest actually doing this. Excel is your friend. Okay. So let's go ahead and see how we do this in Excel. So lambda is equal to 10. Our question was, what's the probability that we get more than 15? All right. So in fact, one way that we can do this is we can say that's equal to 1 minus a Poisson distribution. Here we're looking for 14. Our mean is 10. And in this case, I'm going to say, yes, let's use the cumulative distribution. Okay. So the cumulative will do that sum for us. We don't need to do it. Okay. Okay, so that's a neat thing to do it. So there's one more property, or actually two more things I'm going to tell you. That's sort of neat about the Poisson distribution. Right. So the Poisson distribution it can be applied over multiple timescales, or even fractional timescales. So what I mean by that, in this first problem, we set it up as saying, hey, I get 10 emails per hour. What's the probability I get 6 emails in 1 hour? We could change this time to be, what's the probability I get 6 emails in a day? Or what's the probability I get 6 emails in half an hour? Our Poisson distribution, this equation, actually just gets rescaled in a nice way. So what we're going to say is we're going to put it in terms of a time interval t. Right, and we're going to talk about k events still happening, right? In that time interval. All right, so let's see, the only thing that changed was actually wherever you see a lambda, we've now replaced it with lambda t. Okay, so if I'm talking about what's, again, in 2 hours, what's the probability I get 10 emails? All we have to do is lambda equals 10 here, and t equals 2. Okay, so it scales our distribution linearly, which is really nice. Okay, so if we want to ask, what's the probability of receiving 30 emails in 3 hours? Okay. It's just equal to 10 times 3 to the 30th power over e to the minus 10 times 3, 30 factorial. Okay. So this is a really nice problem, property, that we can either make time longer or shorter, and it just scales that lambda parameter.
This scaling with the expected value be lambda t?
Yes, that's exactly right. So it's almost like you're changing units, right? Instead of talking about how many emails do I get per hour, you're talking about how many emails do I get per 3 hours, right? The one other thing I wanted to mention was sort of what I discussed before. A Poisson does not get approximated by normal. In fact, we go the other way around. A binomial distribution can be approximated with a Poisson. As the number of trials grows large. Okay, so what do we mean by that? So the PDF for a binomial distribution approaches the PDF for a Poisson distribution, where lambda equals n times p. So this approximation holds for a large number of samples. So typically people use 50 or more samples. And n times p is less than 5. Okay. Later on, we'll see where this comes from. It actually comes from the fact that what you're really doing is adding up a number of random variables, and you're doing something called a convolution. If you guys take signals and systems, convolutions will be your friend. But actually, you're convolving probabilities. Okay, with that, sorry guys for going over. Thank you. Have fun.